Next slide. All of the Jovian planets have ring systems, but Saturn's are the most well known because they are easily seen, even with a low power telescope on Earth. They reflect a lot of sunlight because they are made of icy materials, while the other Jovian ring systems are made of much darker material, probably carbonaceous. The next series of slides focus on Saturn's rings, but the principles apply to the other Jovian ring systems as well. Next slide. Because Saturn is tilted with respect to its orbit, we on Earth see its rings from different angles as Saturn moves around the Sun. These images from the Hubble Space Telescope were taken over several years. Next slide. Each major ring is made of thousands of ringlets, and each ringlet is made up of millions of small chunks from micron size to house size. Each particle has its own orbit around the planet, so each particle obeys Kepler's laws of orbital motion. Although modern observations of how radio waves from spacecraft pass through the rings on their way to the command center on Earth, as well as how sunlight passes through the rings, have indicated the size of the particles and how they're distributed, the rings were known to be made of chunks a long time ago from measuring Doppler shifts of various parts of the ring system. The inner particles orbit faster than the outer particles, and the speed decreased outward in just the way predicted by Kepler's third law. Doppler effect observations of various parts of the ring system as far back as 1895 proved that the rings must be made up of billions of small particles. Next slide. The Great Ring Crossing movie is posted on the JPL Photojournal website. The video shows what Cassini saw every time it crossed the ring plane of Saturn. Not only does the video illustrate the extreme thinness of the ring system, it also shows how the angle of sunlight greatly affects what you see. That then tells you about the size of the particles. Larger chunks will block the sunlight, while super tiny chunks will scatter the light forward, like the fine particles on the inside of your car's windshield do when you're driving down the road into the sun. Note that the Cassini division between the A and B rings is about 5,000 miles across. Mercury would fit in it. It looks empty when we view it from above, but when you are underneath the rings, the sunlight angle is different, and you can see then that it definitely has material in it, and the material must be very fine particles. Saturn's rings are incredibly thin. They are 280,000 miles across, but about 100 meters thick, which is about a 1 million to 1 aspect ratio. A typical piece of paper is 1/250th of an inch thick, so an 8.5 by 11 inch sheet of paper would need to be 1,000 times thinner to represent Saturn's rings. Or, if you use the paper's thickness as the scale, the sheet of paper would have to be the size of a football field. The effect of the sunlight angle is dramatically illustrated in the famous image below. This is a view of the night side of Saturn, which is a view you can only see from a spacecraft positioned so that the sun is behind Saturn. The outer part of the atmosphere is illuminated, and from this vantage point you can see the E ring and G ring backlit by the sun scattering off micron-sized particles. The D ring is very hard to see from Earth, but it is easy to see from this vantage point. By the way, the fuzzy E ring is made of water ice particles shot out by geysers on the moon called Enceladus. Next slide. Some of the rings are kept narrow by small moons on the inner and outer edges of the rings. Prometheus, 63 miles in diameter, makes dark drapes in Saturn's F ring. Pandora, 52 miles in diameter, follows. Prometheus and Pandora keep the F ring narrow. Check out the link to see a video of this. Jupiter's ring system also has shepherding moons to keep its black as charcoal rings narrow. Metis and Adrastea keep the gravel and the boulder-sized material constrained in a well-defined ring. Next slide. This graphic shows the 4 Jovian ring systems to the same scale. The next graphic shows the ring system scaled to the size of the planet, which then better shows the proportional size of the various parts of the ring systems in comparison with each other. The pictures note the Roche limit. You cannot have a large moon too close to a planet, or the moon gets stretched apart by the planet's tidal effect, that is, the planet's gravity. That tidal breakup distance limit is the Roche limit. Rings are transient. They last for only a short time, and their structure is constantly changing as moonlets in the rings collide with each other or they get hit by meteoroids passing near the planet throwing off material. Spacecraft measurements of the mass of Saturn's rings and of the rate of dust accumulating on them and of the rate that the particles are falling into Saturn's atmosphere show that Saturn's rings are only about 100 to 200 million years old and will be gone in about 100 million years. Some of the moonlets in Saturn's rings have significant equatorial ridges to make them look like flying saucers. Perhaps these are the result of ring material clumping together,